So given that we know that humans are forming approximate spatial representations that are local and that they do have hierarchical representations, we ask how can the submaps of the local representations be recombined and reused to form hierarchical spatial representations that generalize to representing novel spaces. To answer this question, we take a functional example of human exploration and foraging. Humans are expert explorers and foragers. We can go to a completely new country for a conference, and we are able to find our way in a new city and a new conference venue. So the question is, what computations underlie this cognitive ability? To answer this question, we propose a map induction hypothesis, which suggests that as humans explore novel environments, they're inducing maps of unobserved parts of the environment based on parts of the environment that they've observed, and also based on their prior experiences in familiar environments that are similar to the current environment. For instance, in a berry foraging task, one might anticipate that the landscape of hills will continue in the same fashion, and that the distribution of berries in unobserved spaces would be similar to that observed so far. And more formally, we can think of this as inferring the programs that could have generated an environment given past observations. So to test the map induction hypothesis, we conduct human behavioral experiments in structured environments with rewards embedded into them. We allow the subjects to navigate these environments from a first-person perspective. These subjects do not have access to a top-down map of the environment, and the task given to them is to find the rewards embedded in the environment in a constrained amount of time given to them per trial. To formalize the map induction hypothesis, we build map induction-based generative models that induce maps through composition of map fragments. These models have 4 core components that I'll explain using this toy example. First is the region extractor that extracts region primitives from observed parts of the environment to form these submaps or region primitives. The map generator then uses these submaps and composes them to form map hypotheses based on an underlying probabilistic generative grammar that has transformations like reflections, rotations, and scalings. And this is because humans do have invariant representations. And for instance, when we are traversing in a hotel, the left wing of a hotel is symmetric to the right wing, and they are just mirror images of each other. So having seen the left wing, we can almost predict what the right wing would look like. So that's the gist of the underlying transformations encoded in the probabilistic grammar. And that's what the map generator uses to compose these map primitives to form map hypotheses. The map inference that infers a probability distribution over these hypotheses, which are used by the planner to plan the next steps in the environment in a model-based reinforcement learning setup. So we model this exploration problem as a partially observed Markov decision process where the state is not directly observable by the agent, but is only inferred through a sequence of observations. And POMDP is described as a standard tuple of states, actions, transition function, rewards, observations in the environment, an observation function, and a discount factor. And the optimal agent acts to maximize the expected discounted reward in a given environment. And since we cannot exactly solve a POMDP, we resort to approximate sampling methods like Monte Carlo sampling in order to approximate the solution of the POMCP using the POMCP planner. So we consider 3 model hypotheses: a uniform model that assumes a uniform distribution over the existence of empty space reward or a wall in unobserved parts of the spaces. This model doesn't use map induction, so it has no spatial priors, and you can think of it as using an unconstrained distribution of maps to plan the next steps in the environment. Then we have a maximum a posteriori model or map POMCP model that uses the most likely map out of the hypothesized distribution of maps to plan the next steps in the environment. And lastly, we hypothesize a distributional model that uses all the hypothesized maps generated by the map generator in order to plan the next steps in the environment. And importantly, this distribution can be thought of as a constrained distribution relative to the unconstrained distribution used by the uniform model. Here's an example of the uniform model exploring a space. You can see that the uniform model ends up exploring the space exhaustively because it doesn't have any spatial priors, and hence it doesn't have any expectation of where it's more likely to find rewards. In contrast, the map induction-based models induce the maps of the environment in an online way, updating their estimate of the map based on new observations. And since they have a hypothesized map, they have expectation of where they are more likely to find the rewards. And hence that leads to more efficient exploration relative to exhaustive exploration. Here's another example of a map induction based model, which finds rewards in the partially observed environment. So through experiments, we find that map induction is critical for human-like optimal exploration. In panel A, I'm showing the trajectories of a representative subject from 3 environments used in the experiment. And panel B shows averaged heat maps of all the subjects averaged. So the results show that, as expected, the uniform POMCP model explores these environments exhaustively, whereas the map induction based models explored the environments selectively, similar to what humans do. And if we look at the log likelihood of these models conditioned on human behavioral data, we find that both map induction based models are more likely than the baseline uniform POMCP models. However, this experiment can't be used to distinguish between both map induction based models. Through a subsequent experiment, we find that humans build a distribution of possible maps through map induction. So here we have rewards embedded in environments that are guided by color cues. And we find that the amount of environment observed in this case by humans is closer to the distributional POMCP model. And the log likelihood of the distributional POMCP model conditioned on human behavioral data is much higher than that of the map model. So to summarize, research suggests that humans build a constrained distribution of possible maps through an inductive process by composing map fragments to represent novel parts of the environment. Map induction is a conceptually new way to think about navigation in few and zero shot settings. And map induction significantly improves the exploration performance of the state-of-the-art partially observed Monte Carlo planning.